It doesn't necessarily require an expert to realize that we are witnessing a growing increase in the demand for data, along with constant emergence of new, more advanced network standards. This is what directly led to the denser deployment of base stations to meet network requirements, increased traffic heterogeneity, and introduced additional complexity to the quality of service assurance. This mobile network evolution pushes networks to use techniques that can manage interferences and adapt to traffic in an effort to maintain an adequate network performance. And this is not an easy task for traditional techniques. Scheduling algorithms try to fulfill users' bidirectional uplink downlink requirements while guaranteeing adequate performance. Orthogonal frequency division multiple access is a technique used to separate transmissions of different users in a network while ensuring good network performance. Utilizing time division duplexing in conjunction with OFDMA enables the management of uplink and downlink resources through a flexible switching point configuration mechanism. This allows for jointly determining the switching point configuration and allocating resources in cellular networks. The problem is that joint scheduling algorithms are actually quite complex. In large-sized networks, they can become a challenging problem on the performance, and their scalability and comprehensiveness, among others, compromise their overall performance. The proper assessment of these scheduling algorithms is essential to fully understand their impact on network performance. This impact can be observed through different metrics like throughput, delay, interference, and other quality of service and quality of experience measures. It would be difficult, however, to observe how these variations of different parameters are related to each other due to the unavailability of a comprehensive performance indicator, making it difficult to assess the overall efficiency of a scheduling algorithm. Common approaches in assessing effectiveness attempt to capture performance using single indicators, which only reflects one aspect of the network's operation. A carefully conducted literature survey showed that no benchmark is available in the literature that could be used to objectively assess the performance of a set of algorithms used in communication networks. Also, limited or no investigations are reported to adopt mathematical frameworks that aim to classify and rank algorithms according to heterogeneous properties. In light of all that, Dr. Damaj of Beirut Arab University in Lebanon, Dr. Ahmed Al-Hajj of Beirut Arab University in Lebanon, and Professor Hussein Mouftah of University of Ottawa in Canada proposed the Joint Scheduling Effectiveness Indicator Framework in a research paper titled An Analytical Framework for Effective Joint Scheduling over TDD-Based Mobile Networks. The proposed framework aims to capture the various aspects of joint scheduling algorithms and enable their evaluation, sorting, ranking, and classification. It targets a selection of optimal and suboptimal algorithms. It proposes a systematic and robust procedure for the rapid assessment of a scheduling algorithm for any given network, and presents a discussion on the usefulness and applicability of the developed set of performance indicators in the wider context of computer networks. So how was this framework developed? The development was done using the generic benchmark model of Damaj and Resbah. Accordingly, after defining the goal successfully, the input is identified. It is made up of the targeted algorithms, here a selection of optimal and suboptimal joint scheduling algorithms, and the performance metrics used. The simple performance metrics are classified into algorithmic profile that includes the complexity of the algorithms, network profile that captures the network density and communication interference, and operational profile including throughput, fairness, and base station and mobile station communication interference power. The activity is then identified, here including simulations and validations under MATLAB. In the output element, key indicators are presented. For the first set of indicators, the algorithmic profile, algorithmic complexity is the key indicator. The asymptotic behavior of an algorithm is split into 6 levels that describe the complexity. They range from a logarithmic law at big O of log n till exponential level at omega of 2 power n. These qualitative values are mapped into quantitative values between 0 for low complexity and 1 for high complexity, in order to include them in the development. The network profile set consists of 2 key indicators. The first one is the communication interference, which is the total interference resulting from the adopted switching point configuration, and the other one is the network density. It reflects the scalability of the algorithm, allowing insight on its performance when the network size increases. The operational profile set, which represents how the network balances between satisfying the quality of service requirements and reducing the interference, includes 3 key indicators. The network throughput, in bits per second, whether uplink throughput or downlink throughput. The fairness, which is the faithfulness in satisfying the user's quality of service and quality of experience requirements, and how properly can the algorithm provide an adequate distribution of the resources. And the last one is the base station to base station interference power. That's a critical metric in network operation that should be minimized as much as possible. In the outcome, the combined measure indicators are presented, and they are formulated as the geometric mean of key indicator ratios. The key indicators are combined into their 3 categories as follows. So the algorithmic profile is computed as the ratio of the reference complexity and the algorithm complexity. The network profile is computed as the product of communication interference ratio and the network density ratio. And the operational profile is computed as the product of uplink throughput, downlink throughput, fairness, and base station to base station interference power ratios. Thus, the first and main indicator is the joint scheduling effectiveness indicator, computed as the geometric mean of the 3 profiles. Other than JOSI, 5 more indicators are computed from the key indicators to help capture all the sides of the algorithm performance. The network profile indicator, which captures the performance with respect to size, and is better when the interference does not increase dramatically as the network size increases. Operational profile indicator, that is best when throughput and fairness are high and interference is low. And algorithmic profile indicator. In addition to the reliability indicator, which captures the reliability of joint scheduling in terms of interference and traffic adaptability. And lastly, the base station to base station efficiency indicator, that helps capture the efficiency of joint scheduling in terms of throughput and interference power. Coming to the performance, to analyze the performance of an algorithm based on the JOSI system, all key indicators are assigned values that fall into 4 levels of performance: low, somewhat satisfactory, satisfactory, and high. Based on them, the combined measures indicators are calculated. The JOSI then enables sorting algorithms according to their effective performance. But capturing an attained performance level requires additional information about key indicators. Thus, 2 evaluation schemes beside JOSI are created to enable ranking and classification of an algorithm according to performance effectiveness. One scheme is based on aggregate numerical measures and comprises the mean, standard deviation, kurtosis, and skewness of ratios that aid that judgment. Another scheme, indicator status scheme, comprises percentage of satisfaction that equals the percentage of key indicators that attain a rank of satisfactory and above, which also helps in classifying an algorithm with more accuracy. The classification occurs based on charts comprising 4 performance levels: highly effective, effective, somewhat effective, and ineffective. The paper considers 3 joint scheduling techniques: the full synchronization approach adapted in TDD-LTE networks, the full coordination approach, and the cluster coordination scheduling technique that's used here as a benchmark. Approaches are simulated on MATLAB under the same network conditions for a network of 30 cells. The evaluation results presented in figures reflect the network performance under each of the simulated joint scheduling algorithms. As expected, the full synchronization algorithm achieves highest scores considering it has the lowest algorithm complexity in addition to base station interference elimination, especially since operational profile indicator, network profile indicator, and reliability indicator majorly depend on the resulting interference in the network. Full coordination technique is relatively close to full synchronization one, and in base station to base station efficiency indicator, full coordination outperforms since it tries to find the sweet spot in terms of quality of service assurance and network performance optimization. Cluster coordination indeed ranks worst in all cases. Classification outcome based on the described aggregate numerical measure scheme shows a high percentage of effectiveness for the fully synchronized scheduling technique. The indicator status scheme classification captures the performance trade-off in the full coordination case in a better way and shows that it outperforms the full synchronization algorithm for a large number of cells in the network, illustrating the high level of satisfaction achieved. The absolute difference between the two classification schemes is highlighted through the difference in classification metric, ranging from small at level 0 to somewhat significant at level 1, only in a couple of cells, which is in fact a very good sign, and in all, the results confirm the competition between the full synchronization and the full coordination schemes in achieving the best performance classifications. These results showcased a novel benchmarking mechanism for scheduling algorithms that captures the implications of the adopted algorithm on the network performance. And without it, measuring the impact of a scheduling algorithm becomes harder as the relationship among different network metrics cannot be clearly seen.